Hello everyone, welcome to another video. In this video, I'm going to talk about some more SRE interview questions and answers. And as you can see, this is part 5 of the series which I already have. So there are already 4 videos uploaded. Do check those as well. And this is part 5 and I'm going to keep coming with a lot of videos like this in the future. Alright, so let's get started. And I have our question number 1. What happens internally when a Kubernetes pod gets OOM killed or out of memory killed error message? This is a very common interview question. And also when you're working for a company, you will see this message a lot. So here the interviewer wants to understand whether you know the series of events that happen behind the scenes and your pod reaches this message. Okay, so let's see the answer now. OOM killed happens when a process inside a container exceeds its memory limit, which is enforced by Linux C groups or control groups. Before I go any further, I just want to talk about this memory limit also. So here I have the official documentation page from Kubernetes. So it is on kubernetes.io. And here you can see I have a pod YAML manifest file where inside your container spec section here, you will see resource request and resource limit. So this resource limit is the one that is going to set the boundaries to your container process on how much resources it can consume at max, okay, at maximum. So here you see these limits on memory and CPU. So these are the hard limit that your container can reach. Okay, so let's go back to answer now. So when you define a memory limit in Kubernetes, the container runtime creates a control group for that container. A control group or a C group is a Linux kernel feature that isolates and limits resources like memory and CPU for a group of processes. This control group sets a hard memory boundary for all processes running inside the container. If the application tries to allocate memory beyond this limit, the Linux kernel is going to detect it. Okay, and it's going to see that your C group has exceeded its allowed memory. So this memory is the same that I just spoke about in this YAML manifest file. So this is the limit that I'm talking about here. So if the application tries to allocate memory beyond this limit, the Linux kernel detects that the C group has exceeded its allowed memory. At that point, the kernel invokes the OOM killer. So this is the thing that is invoked by your Linux kernel. It's an inbuilt mechanism that selects a process to terminate in order to reclaim the memory. It uses factors like memory usage and out of memory score to decide which process to kill. And typically it kills the main application process inside the container. The process is terminated by sigkill. So this is the signal that is passed to the process, which cannot be caught or handled. So the application stops immediately. This causes the container to exit with code 137. This container runtime reports this to the kubelet, which then updates the pod status to OOM killed and restarts your container based on the configured restart policy. So let's talk about the restart policy also in Kubernetes. So by default, Kubernetes uses a restart policy of always, which means that your kubelet is going to restart your container inside the pod, not the pod itself. And if the issue persists, the container may restart repeatedly and the pod can enter a crash loop back off state as well. So this is the answer that you need to explain. So maybe I have added like a few more details, but I just wanted to break it down into small pieces of information linked to each other so that you understand each and everything that happens behind the scenes. If you want, you can make this answer more compact. Okay, but I think if you are able to understand this, I think you can explain this in your own words also. Okay, so this is the answer to question number 1. So question number 2, how do you handle Terraform state file locking and consistency in a large team? So here the interviewer just wants to understand whether actually you have used a Terraform in a company and where multiple teams are using your Terraform config. So how do you explain this? So you can say, so before I start the answer, I'm talking about when you use a Terraform with AWS here. So I'm going to take the example of AWS cloud, but the things are going to be similar if you use any other cloud as well. So in large teams, I maintain Terraform state consistency by using a remote backend like S3 with DynamoDB for state locking, which ensures only one operation can modify the state at a time. So this DynamoDB state locking is only applicable till 1.10. Okay, so if you are using a Terraform version starting 1.11 and beyond, then Terraform can manage the state locking for you as well. So you do not need to use DynamoDB there. Okay, but I'm just talking about this version because my company is still using 1.10 as I record this video. But I think the upgrade is about to happen, and we're going to move to version 1.14 as the bare minimum version. So I'll talk about it when I have that done in my in my environment. So right now we are using 1.10 and we are using DynamoDB for state locking. So in large teams, I maintain Terraform state consistency by using a remote backend like S3 with DynamoDB for state locking, which ensures only one operation can modify the state at a time. I avoid concurrent applies by enforcing CI/CD based execution, where all Terraform runs go through a centralized pipeline trigger via pull requests. So here I'm talking about how I'm able to implement this in the CI/CD pipeline environment also. So what happens whenever you are making any changes to the main repo? So in the main application repo, you will have one protected branch, which is either your main branch or your master branch. So any change to that is going to go through a merge request. So we create another branch, we make the changes to the new branch, and then we raise a merge request to merge that branch into the main branch or the master branch, depending on what is your protected branch. So this is the way we are able to control that whenever we have any Terraform based changes. In that case, only one pipeline is going to run at a time. Okay, so this is going to create a single writer model, adds approval gates, and provides auditability, preventing multiple engineers from modifying state simultaneously. To reduce lock contention and blast radius, I split state files by environment or service. For example, separate states for networking, EKS, and applications across dev, staging, and prod. This ensures teams can work independently without blocking each other and limits the impact of failures. I also enable S3 versioning for recovery and handle stuck locks by inspecting the DynamoDB lock entry and using force unlock carefully when needed. So I just explained about how we are using the concept of merge requests and branches when we are using CI/CD pipelines for Terraform based deployments. I also want to explain this bit in a little bit more details. Okay, so I have already written this so that you can also revise it whenever you need it. So instead of keeping all infrastructure in one big Terraform state file, which we don't want, we split it into smaller state files based on the environment or service. So for example, I keep separate state files for networking. For example, you have a VPC, subnets that you want to deploy. So you keep it in a separate state file. You have EKS cluster or all the resources in your EKS. So for that, you can keep a separate state file, and applications also. And also you try to separate them across dev, staging, and production. So this helps because only one person can modify a state file at a time due to locking. If everything is in one single file, it's going to block each other and it will make things very delayed. Okay, so that's not what we want. So we want a better way where we can manage these different state files separately. At the same time, we are able to run our pipelines parallelly if it is for different services or different environments. So when state is split, different teams can work independently on their own parts without waiting. It also reduces risk. If something goes wrong in one state file, it only affects that specific part instead of the entire infrastructure. So this is going to make your changes safer, faster, and easier to manage. Then here's the example of a state file with where you have a backend in S3 and you have a DynamoDB table. So this is how it's going to look like, and you will generally define this configuration in a file called backend.tf file. So there you define your backend configuration. Okay. So yeah, so that's how you can explain this answer. Once again, I've given you every detail possible relating it to how I manage in my current company, so that you are able to explain it in that way. Question number 3. What are the 4 golden signals you would monitor for a high traffic API as an SRE? So once again, very important topic. I already have a video where I've spoken about it in much more detail, and there's a hands-on demo as well. You can check that video as well. In this video, I just want to talk about how you're going to answer it in an interview. So the 4 golden signals are latency, traffic, errors, and saturation. These are the most important metrics to monitor for any high traffic API because they give a complete picture of system health. So this is where it's going to help us. And as I mentioned, I have a video where I've spoken about it in much more detail. I have a hands-on demo as well, and you can check that video. Latency tells us how fast the API is responding. Instead of just looking at averages, we focus on percentiles like P95 or P99, which show how slow the experience is for real users. For example, if your API usually responds in 100 milliseconds, but P99 latency goes to 2 seconds, some users are still having poor experience. I would like to emphasize on this example that I've taken to explain you the concept of P99 latency here. So P99 latency means, as an example, if we take 100 requests. So out of 100 requests, 99 requests are getting processed without any latency. But there is one request for which the latency is up to 2 seconds. Okay. So all I'm saying is if you take 100 seconds, out of those 99 requests are being processed in only 100 millisecond, which means that 99% of the users are not facing any issues, but one user out of every 100 user is impacted here. So which means that for that 100th user, the latency is 2 seconds. So it means that most of your users, everything is fine in terms of latency, but that one user is still there, which is impacted. So we need to take care of that as well. Okay, so even though your entire system it's looking healthy, but even then there are few users who are impacted right now, and they will not have the best of experiences in terms of your application performance. So this is where this P99 latency calculation is really critical for us. Then traffic tells us how many requests the system is handling, usually measured as request per second. This helps us understand load. For example, during a sale or peak hours, the traffic may suddenly increase, putting pressure on the system. Okay, so traffic is going to tell us how many requests our system is handling, and usually measured in requests per second. And yes, the traffic is going to be different at different hours. So if we talk about an e-commerce website where you have a sale running, so in those periods where you have sale running, you will have higher traffic as compared to other periods of time where there is no sale. So this is obvious. So this is just to see how much is being coming to your application, how much traffic is coming to your application. Then errors represent failed requests such as HTTP 5xx responses or timeouts. A rising error rate is a direct signal that something is broken. For example, if your error rate jumps from 0.1% to 5%, it likely indicates a deployment issue or a failing dependency. So this is how you can explain the third golden SRE signal called error. Then the last one is saturation, which shows how close your system is to its capacity. This includes metrics like CPU usage, memory usage, or database connections. For example, if CPU usage reaches 95%, the system is near its limit and may soon start slowing down or failing. So this is where we try to calculate how much capacity we have available on our nodes. So if I take the example of an AWS EKS cluster where you have multiple worker nodes, so you want to check how much is being consumed in terms of CPU and memory specifically, and how much is available. Okay, so this is where you can create a saturation based dashboard panel, which is going to show you the detail of that. A real world example, if I want to think about all of this, Imagine your API receives a sudden spike in traffic during a product launch. As traffic increases, CPU usage, which is going to be your saturation, it's also going to increase. Once the system gets close to its limits, latency starts to rise because requests are taking longer to process. If the pressure continues, the system may begin to drop requests, leading to increased errors. By monitoring all four signals together, you can detect the issue early and scale your system before it's going to impact the users. So this is where we use these four golden signals in SRE: latency, traffic, errors, and saturation to be able to achieve this. Okay, so this is how you can explain this question. Question number 4. How do you manage high cardinality in Prometheus metrics? So in Prometheus, we know that for every metric plus label combination, it's going to create a separate time series. So the more labels means that your time series database is going to be huge, which means that it's going to consume a lot of CPU and memory, which we don't want. So that is called high cardinality. So we would want to reduce it. So let's see how we can answer this question in an interview. So high cardinality in Prometheus happens when labels have too many unique values, which creates a very large number of time series. In Prometheus, every unique combination of metric name and labels becomes a separate time series. So if a label has unbounded values, the number of time series can grow very quickly and it can impact performance. As an example, if you are using this type of metric where you are using HTTP request total for each user ID. So you see here, this user ID is varying here, and just assume that the value of this user ID is in millions, which means that you can have millions of different values for user underscore ID here. So this is going to create millions of time series as well. So this will increase the memory usage and it's going to result in slow queries, and it can even crash your entire Prometheus instance. So to manage high cardinality, the most important step is to avoid using high cardinality labels such as user ID, as we just saw in this example. Apart from that, you can also have a session ID, a request ID, or an IP address that will, in most cases, will have a lot of values. Instead, we will try to use a stable and low cardinality labels like endpoint, HTTP method, or a status code. Okay. Then there's one more example if I want to talk about HTTP request total. Endpoint is equal to /login, method is equal to post, status is equal to 200. So you see here, I'm trying to filter out the values that I may have using this type of metric. Okay, so this is a way you can reduce high cardinality in Prometheus. So this is going to keep the number of time series limited and meaningful. Another approach is to use aggregation instead of tracking every individual value. Instead of tracking per user, we aggregate at the service or endpoint level using queries like sum rate HTTP request total 5 minutes by endpoint. So this is another way by which you can reduce high cardinality problem in Prometheus. This is going to reduce the amount of data and it's going to make your queries much faster. In production, I also enforce laying guidelines so developers don't introduce high cardinality labels, and I treat metrics design as carefully as application code. In summary, I manage high cardinality by avoiding unbounded labels, aggregating metrics at a higher level, dropping unnecessary labels using relabeling, and continuously monitoring the number of time series to prevent performance issues. So this is how you can answer. Okay, if you see here, this answer has 3 slides, but I can go on and on and on. Okay, but as I mentioned, these answers are relevant to interviews. So in interviews, you are only going to get like 2-3 minutes to explain. So I think this is good enough with an example. If you can explain like this, the interviewer will be able to understand that you've actually managed these in production. All right. So these are the 4 questions I want to cover. The video is getting too long, so rest of the questions I'm going to cover in the next video. Alright guys, I hope you liked the video. As I mentioned earlier that I have multiple playlists. I have a lot of content on my channel. I have a YouTube membership as well, where I'm sharing some really good premium content that you will not find elsewhere. I have videos on how to configure SLI, SLO, SLAs, okay, in Prometheus and Grafana. So I mean, I have a hands-on demo on that. I have hands-on demo on using the Prometheus and Grafana matrix with open telemetry data for a Java Spring Boot application. There also I have explained everything in detail, and I have a hands-on video on that. I have a hands-on video on SRE Golden Signals as well. So do watch those videos. It's going to immensely help you in your interviews. Alright guys, that's all for this one, and I'm going to see you in the next one. Bye for now.